Today we're going to talk about determinants of order 2. But before we do so, let's do a quick review of Gaussian elimination. Here's a series of steps to arrive at a matrix B that is in reduced row echelon form. First, let's start with the matrix, but let's say that we have a cursor entry. That just means we're at some position in our matrix. If this entry is 0, then we're going to swap with the row below that has a non-zero entry so that we can play around with making this a pivot. Just interchanging with the row below is what we call a type 1 operation. Now that we have a non-zero entry, we'll divide all of the entries in this row by this non-zero entry to make this non-zero entry equal to 1. This, of course, says now that in our row we have a pivot. Dividing everything by a non-zero element is what's called a type 2 operation. Third, let's now eliminate all of the other entries in this column by subtracting away suitable multiples from this row. This, of course, is a type 3 operation. Finally, once we've done this, we'll move the cursor down one row and over to the right one, and then perform these steps all over again. Starting with an m by n matrix A and arriving at this matrix B in this way is what's called Gaussian elimination, and this matrix B is what we say is in reduced row echelon form. Let's say that we have an m by n matrix A, then its transpose is that n by m matrix where we just simply interchange the rows of A and make them the columns of A transpose. Recall that the column space of A is that subspace that literally is generated by the columns of A. That is simply spanned by the columns of A. Here you'll see that we've placed in red the first column of A, the entries A11, A21 through AM1, and we can also see where it appears as a column vector in the span of the column space of A. We'll say that the row space of A is that subspace generated by the rows of A. It's a little bit easier to see this if instead of looking at the rows, we see the columns of A transpose. For example, here in red, you see that we've marked out at the top of your screen the first column of A transpose, A11, A12 through A1n, and at the upper right of your screen, you see that this is the same as the first row of A. At the bottom of your screen, you see that we've placed now the first column of A transpose as part of the span for the row space. Here are a few results that are not listed in the textbook, but we will use them later. Again, say that A is an m by n matrix, and let's let B be the reduced row echelon form of A. Finally, let's let S denote the collection of pivot columns of B. That is, they'll just be those columns where we have pivots. The row spaces of A and B are the same. Next, our set S is a basis for the column space of B. Third, the number of elements in S is the rank of A. And finally, let's say that M equals N. Then A is invertible if and only if its reduced row echelon form is the n by n identity matrix. As a warning, even though this statement says that the row spaces of A and its reduced row echelon form B are the same, this is not true for the column spaces. We'll come back and discuss an example of this later. But for now, let's give a motivating example on why we might want to do all of this. Let's consider a system of linear equations in the following form. Here we have two equations and two unknowns, x1 and x2. Assuming that this quantity, a11 times a22 minus a12 times a21, is non-zero, then we know that we can find the unique solution, S, as follows. First, let's express the system of equations in the form a times x equals b in terms of the matrices that you see here on your screen. We've seen in previous lessons that we can compute now the inverse of this 2 by 2 matrix A by just dividing by this quantity that we introduced earlier, a11 times a22 minus a12 times a21. In particular, by looking at some examples from previous lessons, we see that our desired solution, S0, is simply A inverse times B. this two-dimensional vector that you see at the lower right of your screen. This is our solution, x1 and x2. We'll express all of this in a slightly different way by looking at this quantity we introduced before. This will allow us to define determinants. This quantity, a11 times a22 minus a12 times a21, is called the determinant of our 2 by 2 matrix A. Here's one of the main results. If A is a 2 by 2 matrix, then it is invertible if and only if the determinant is non-zero. Let's give a proof of this. First, because A is a 2 by 2 matrix, let's write it out in the way you see here on your screen. A11, A12, A21, A22. Recall that, by definition, our matrix is invertible if and only if the left multiplication by A map is an invertible linear transformation. Let's first assume that the determinant is non-zero. It is easy to check that the 2 by 2 matrix you see on your screen is the inverse of our matrix A, because A times the matrix, this is matrix times A, is the 2 by 2 identity matrix. This means that if the determinant is non-zero, then our 2 by 2 matrix A is indeed invertible. Conversely, let's assume that A is invertible. We need to prove that the determinant is non-zero. By way of contradiction, let's say that the determinant is 0. I'd like to consider the following two matrices, U and V. Here, U simply looks like it's coming from the first column of A inverse, and V sort of looks like it's coming from the second column of A inverse. I've chosen these two vectors such that A times U should be the 0 vector, and A times V is also the 0 vector. Again, remember that we're assuming our determinant of A is equal to 0. This means that both U and V must be in the null space of this left multiplication by A. However, because we're assuming that A is invertible, this means that left multiplication by A is also invertible, which means that the null space of this linear transformation must be the trivial subspace. That means that the only vectors that lie in the null space must be the 0 vectors. So U and V must be the 0 vectors, which means that each of the 4 entries of our matrix A must be 0. Showing, of course, that A is the 0 matrix. But of course, the 0 matrix is not invertible, so we have a contradiction. This means that our determinant must be 0. We'd like to give a geometric interpretation here of the determinant. To this end, let's say that U and V are two vectors in the real plane R2, any two vectors that you like. Let's let A be that matrix that we form by placing U and V as the first column and the second column. Geometrically, let's take a look at the parallelogram determined by these two vectors U and V. You can see the graphic here on the screen where we have U as the blue arrow and V as the red arrow. Our section P, our parallelogram, is just the region in between these two red arrows and these two blue arrows. The statement is that the area of this region is the absolute value of the determinant of A. In particular, the determinant is 0 if and only if the vectors U and V are parallel to each other. Intuitively, it looks like they're sitting on top of each other. Moreover, for any 2 by 2 matrix A, we have the following curious identity that you see at the bottom of your screen. Here we have the sums of squares is equal to the products of the sums of squares. The second statement is also often called Lagrange's identity. Before we get into the proof, let's maybe draw a few pictures to explain what it is we're going to do here. Remember that U and V are just two vectors in R2, any two vectors that you like. What we'd like to do first is try to discuss the area of this parallelogram. This will correspond to the blue shaded region you see here at the bottom of your screen. Of course, we can always slide things around so that this blue shaded region really does look like a rectangle if we just move the yellow shaded regions in the right way. The whole idea here is that the area of the parallelogram is simply the length of the base, b, times the height, h. And of course, the height we can determine by looking at the length of the hypotenuse for the yellow region times the sine of the angle theta. So again, we're going to try to compute the area here of the parallelogram by looking at the length of the base, b, and then the height, which will somehow involve the sine of a certain angle. So let's try to prove the first statement. To this end, we'll express everything using polar coordinates. That is that we have lowercase r, which is the length of the vector u, and capital R, which is the length of the vector v. Alpha is just the angle that the vector u makes, and beta is the angle that the vector v makes. Of course, if beta and alpha are angles, then the angle in between the two vectors, the angle theta, is just beta minus alpha. So we have a parallelogram whose base must be length lowercase r, again this is the length of the vector u, and its altitude must be the length capital R times the sine of our angle theta. Capital R, of course, is the length of the vector v, and beta minus alpha is the angle between the two vectors v and u. So the area, as stated on the previous slide, is just the base times height, or lowercase r times capital R times sine beta minus alpha. On the other hand, let's take a look at the determinant of our matrix A. If we simply place in the two columns of A in terms of u and v, and again in terms of lowercase r, capital R, alpha, and beta, then we can just compute the determinant of A by using a formula which is just the sine of the difference of two angles. So by using some trigonometry, we can express the determinant of A as lowercase r times capital R times sine of beta minus alpha. This means that the absolute value of the determinant of A must be the area of our parallelogram. Again, we simply have done this by using polar coordinates and just a little bit of trigonometry. It's clear now from the way we have all of this set up that this parallelogram has area 0 if and only if beta equals alpha, if and only if the two vectors u and v are parallel. That is, that they make the same angles. For the second statement, it's just a matter of realizing that we just have sine squared plus cosine squared equals 1. The first quantity, this a11, a12, plus a21 times a22, we can write in terms of the cosine of theta by just using the polar coordinates from above. Similarly, we've already worked out that the determinant a11 times a22 minus a12 times a21 is expressed in terms of the sine of the angle theta. The rest of this is just algebra. We'll remark that in general, we're going to wish to define the concept of a determinant in order to generalize these three key results. Here's what we'd like to do. Let's let A be any n by n matrix, not just the 2 by 2 matrix. Eventually, we'd like to show the following three statements. First, a matrix A is invertible if and only if its determinant does not equal to 0. Second, let's let S be the set that consists of the different columns of our matrix A. Then we can form a parallelogram in terms of these columns, and we'll show that the area, really the volume, more generally what we call the hypervolume, is simply the absolute value of the determinant of this matrix A. If and only if, we'll actually show that the determinant is 0 if and only if S itself is a linearly dependent set. And finally, we'll have a slight generalization of Lagrange's identity. This says that given any two columns P and Q of A, we can take a look at the sum, which you see on the left, plus the sum of the squares, which sort of looks like the entries of a determinant, should be the products of the sums of the squares. We'll try to explain this last identity as we move on throughout the course. But I'd like to end today with a slight teaser about what will happen for 3x3 determinants. Let's first try to do a visual reminder of what happens for 2x2 determinants. When n is equal to 2, recall that we have a 2x2 matrix and its determinant, a11 times a22 minus a12 times a21. There's a simple mnemonic for this expression. We'll place the 4 entries of a matrix in terms of what you see here on your screen, a11, a12, a21, a22. Now we'll place in arrows and we'll simply multiply the numbers together along the arrows. But we want to add and subtract depending on the orientation of the arrows. So for example, a11 times a22 is moving from upper left to lower right, so we'll add this for our determinant. Whereas a12, a21 is moving from upper right to lower left, so this will correspond to subtracting from our determinant. So literally the determinant says take the first arrow going from upper left to lower right, a11 times a22, minus the second arrow from upper right to lower left, a12 times a21. So again, this gives us a visual representation of what a determinant of order 2 will look like. Let's take a look at the case when n is equal to 3. Now here we have a matrix with 3 rows and 3 columns. We'll define the determinant as you see here on your screen. We'll explain why in a future lesson why we make this definition. But for now, we'll say that we can remember this using the following diagram. Here, we haven't just written the 3 columns of A, but we've actually written so that we have 5 columns. As you read the columns, you'll see that the first 3 columns, going from left to right, are the first 3 columns of A. But then the latter 2, we've repeated the first 2 columns of A all over again. So again, our 5 columns look like the first column of A, second column, third column, first column again, second column again. Once we have these 5 columns, we can now draw in a series of 6 arrows. The first 3 you'll see go from upper left to lower right, and the latter 3 go from upper right to lower left. We're now going to add and subtract these depending upon the orientations of the arrows. For example, we take the first 3, that will be the product a11, a22, a33. We'll add this to the determinant. For the next 3, a12, a23, a31 will continue to add. And then for the next 3, a13, a21, a32 will continue to add. But now we have 6 arrows going in the opposite direction. a12, a21, a33 will subtract. a11, a23, a32 again will subtract. And finally, a13, a22, a31 will subtract. So again, for our determinant, we actually have 6 different expressions, and we'll either add or subtract depending upon the orientation of the arrows. In the next lesson, we'll discuss how to use these concepts to define a determinant for any n by n matrix. Thanks for watching.